Hello, class. Welcome back to microbiology. You are in part 2 of chapter 2. We're going to talk about solutions and acids and bases and how molecules act in a cell. So water is a pretty important molecule. It is the basis of life. It is what we have on Earth. Most of the Earth is covered with water. It has lots of important qualities. One of them is that it's very soluble. It's able to make solutions. A solution is when you mix two or more substances together. So Kool-Aid mixed in water, salt mixed in water to make the ocean, paint thinner mixed with paint. These are all solutions. Two different substances mixed together. In a solution, you usually have some medium that is doing the dissolving and something that is being dissolved. So the solvent is the liquid or the air that's being dissolved in. Water is a really good solvent. A lot of things can be dissolved in it. Salts can be dissolved in it, sugars, anything that's polar, anything that can form any sort of hydrogen bonds or ionic bonds are pretty easily going to dissolve in water. The solute is whatever's being dissolved. So it could be a salt, it could be a sugar, it could be, your proteins, whatever is being dissolved. When you have a solute dissolved in your solvent, you end up with a solution. These two things mixed together. Water solubility, or the solubility of any solution, tells you how capable it is to dissolve something, how easily a solution can be made with that particular solvent. Some particular qualities that water has in making an aqueous solution being a solution using water. One is water is able to ionize or dissociate molecules. So ionic bonds are going to be broken whenever water is around because water is very polar. The hydrogen end is going to be a little more positive charge and the oxygen end is going to be a little more negative charge. This should be something you talked about in your prerequisite classes, so this should be something that you're already familiar with. And if it's not, your textbook does discuss it some more, and you can always come talk to me during office hours or email me so that you can be keeping up with what we're talking about today. Okay, so water is able to dissolve ionic bonds because of how polar it is, so it has very good ionization ability. Then when something dissolves around water, if it's ionic or polar, the water molecules will surround it. It'll give it this little blanket of water around it called a hydration sphere. So any liquid or any substance that is going to dissolve in water is called hydrophilic. So hydro meaning water and philic meaning loving. So water loving. So anything that interacts readily with water molecules, things like ions and polar molecules, are going to be hydrophilic. This would be not things like oil. Oil does not mix in water, so oil is not hydrophilic. But if you have a block of glucose, it'll dissolve. If you have a packet of Kool-Aid, it'll dissolve. These things are hydrophilic. They readily dissociate in water. So here you can see salt, NaCl, which is a crystal of ionic bonds, your sodium and chloride ions. And here your chlorine ion, which is the negative charge, is interacting all with the positive blue ends of the water molecule. Your sodium ion with the positive charge is interacting all over with the negative oxygen ends of the water molecule. So you have this hydration sphere around it, this water covering it. Even if your molecule is not ionic, but it's polar, like this glucose or sugar molecule, you can see the water surrounds it. Some areas with its oxygen end and some areas with its hydrogen end. Because that polar molecule is going to have partial positive and negative charges around it also. A lot of molecules can give up a hydrogen ion. So that hydrogen ion is going to be released as an H+. H+ is something that is very, very reactive. It will break bonds. It will just degrade anything, break it down. It'll change the shapes of molecules. If it's in a cell, it is going to wreak havoc on your cell. It will destroy your tissues. So in your body, we closely regulate this with buffers to stop this from happening. Any excess H+ will be picked up. Water can dissociate a little bit to form H plus or hydrogen ion and OH minus or a hydroxide ion, but these are typically going to be in balance with each other. It's when you start having too much H plus or too much OH minus that you're going to start having some crazy havoc going on in your cells. So we keep those closely regulated so that we don't have craziness breaking down our cells. The pH of a system will tell you how much hydrogen ion it has, what its concentration is, how much is in that solution. When you have a neutral pH, your hydrogen and your hydroxide ions are balanced. So neutral pH is 7.0. The pH of human blood is 7.3 to 7.45, so that's pretty neutral, pretty close to 7. As things get lower than 7, it becomes pH. As a pH gets lower than 7, it becomes more acidic. And the lower it gets, the more acidic it is. But pay attention to this relationship here. The lower the pH is, the higher the hydrogen is. So as the pH is going down, hydrogen is going up. So something with a pH 4 and something with a pH 2, the pH 2 is a lower number, so it has more hydrogen. The lower it gets, the more acidic it is. And then the opposite is true. As it gets higher than 7, the more higher it gets, the more basic it is. And as the pH goes up from 7 to 8 to 9 to 10, you're getting less and less hydrogen in there. So the greater the number is, the lower the hydrogen concentration is. So something with a pH of 10 and something with a pH of 13. The pH of 13 has drastically less hydrogen ions than the pH 10 because 13 is a higher number, so the hydrogen is less. So your pH scale has an inverse relationship with hydrogen. The higher the number, the less the hydrogen. The lower the number, the more the hydrogen. pH scale goes from 0 to 14. So 0 to 7 is acidic, 7 is neutral, 7 to 14 is basic. So if you were to look at this, pH 7 would be pure water. As you go down more and more, we're getting more and more hydrogen ions. So something like saliva or milk is a little bit acidic. Grapes and tomatoes have a pH of 4. They're mildly they're decently acidic. Beer, vinegar, wine, pickles, they're definitely acidic. Stomach acid is very acidic. Back to 7 where it's neutral. As we get higher and higher, we're getting more basic. We're having less and less concentration of hydrogen ions. So eggs have a pH of almost 8. Ocean water, about 8.5. Household bleach, almost 10. You're getting less and less hydrogen ions. You're getting more and more hydroxide ions. And one thing to notice, I'm not going to ask you to tell me the exact hydrogen concentration, but it is nice to be able to tell how one pH compares to another. And so for every one change in pH, you have a 10 times change in hydrogen ion concentration. So if we go from 6 to 5, you have 10 times more hydrogen. If you go from 6 to 4, you have 10 times 10. You have 100 times more hydrogen. If you go from 8 to 11, you have 10 times 10 times 10. You have 1,000 times less hydrogen concentration. Okay? So if you're moving from tomatoes, here about 4, to beer at pH of 3, which one of those has more acid? Which one of those is more acidic? So the lower number tells you it's more acidic. Which one of those has more hydrogen ions? Again, the lower number tells you more hydrogen ions. And how much more does it have? You'd say one change in pH means 10 times more. What if we are going from ocean water about pH 8 to ammonia pH 11? Which one has more hydrogen ions? The ocean water has more hydrogen ions. Ammonia has more hydroxide ions. Which one is an acid or a base? They're both a base. And then how much more hydrogen ions does ocean water have compared to ammonia? You say 10 times 10 times 10 is 1,000. 1,000 times more hydrogen ions for ocean water. 1,000 times less hydrogen ions for ammonia. Okay, that's a very common question. I'll throw on a quiz or an exam. Please make sure you can understand how to do that. So an acid is going to be anything that donates hydrogen ions or donates a proton, because really an H plus is a proton. So anything that dissociates in the solution and releases hydrogen ions is an acid. If it's a strong acid, it'll dissociate completely. It'll release all of its hydrogens. A weaker acid will dissociate partially and release part of its hydrogen ions. A base is the opposite. It's a proton acceptor. It's something that will remove hydrogen ions from solution. They're typically going to dissociate to make a hydroxide or an OH minus. That OH minus will interact with your H plus and make water. A strong base will dissociate completely in solution. It'll take out all of the hydrogen ions that it can. Then weak acids and weak bases will not dissociate completely. They'll dissociate partially. So here, like this carbonic acid can give up a hydrogen, but it can also hold on to a hydrogen. It can pick up a hydrogen. It can release a hydrogen. It can release two. It can pick up a couple. So by being able to do this, by not completely dissociating all the time in all situations, it helps to balance the pH. If there's a little bit extra hydrogen around, it can pick it up. If there's a little bit too few hydrogen ions, it can dissociate this one and allow that to be released. So weak acids and weak bases are nice to balance the pH. Salts are going to be any solids that dissociate into cations and anions, anything except hydrogens and hydroxide. So NaCl dissociates into Na plus and Cl minus. Neither of that is hydrogen, neither of that is hydroxide, so that's a salt. But first, we were just talking about stabilized pH, because they can both remove and replace hydrogens. They can pull hydrogens out from a strong acid. They can release hydrogens if it's a strong base. In the human body, sodium bicarbonate is very important to help buffer. It buffers carbonic acid, which is an acid that can form in the blood when your blood picks up carbon dioxide. So that keeps your blood at a very basic pH. You may have also heard of antacids. You may have taken antacids before. Antacids are anti-acid, so they are basic compounds that will neutralize acid, especially if you have a lot of stomach acid causing reflux. You can take an antacid and it'll neutralize that acid, something like Tums or Rolaids. Okay, so here's a reaction. Antacids can neutralize acid by this following reaction. Magnesium hydroxide plus 2HCl will make magnesium chloride plus 2 water. So in there you have an acid, a base, and a salt. I'll give you a hint to get you started. This water is water. It's not acid, base, or salt. These three, one of those is acid, one of those is a base, and one of those is a salt. Also, at this point, you should be able to tell me why the polarity of a water molecule is important. Okay, I will see you back for our next section where we're going to start talking about the organic and inorganic compounds, what that means, and some of the big biomolecules that are going on in our cells. I'll see you later. Bye.